Hello everyone, welcome to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. We have discussed transistors, that is one type of transistors. They were called BJTs, bipolar junction transistor, and we know that they were classified into NPN and PNP. Then we saw the characteristics. After that we saw the applications, then biasing, then the analysis, both the DC analysis and the AC analysis of our amplifier circuits. Today we are going to discuss a new device, and that device is called FET or field effect transistor. Now the device I am going to introduce today is called junction field effect transistor, and there is one more FET we have to learn, and that is called MOSFET, metal oxide semiconductor FET. Today we will discuss the construction and operation, that means the characteristics of a junction field effect transistor. Shall we start? A junction field effect transistor, or generally an FET, is a three-terminal device. So just like a BJT. Then we know that a BJT is a current control device, but in FET is a voltage control device. And you know that BJTs are classified into NPN and PNP transistors. Same way FETs are classified into N channel and P channel FETs. Another thing about FET is it is unipolar. Unipolar means in FET has one type of charge carriers, either electrons or holes. There is no minority charge carriers, there are only majority charge carriers, and the conduction is because of only one type of carrier. Then these FETs have very high input impedance. And this high input impedance is a very important characteristics in the design of linear AC amplifier systems. But the difference between FET and BJT is that the output characteristics of BJT is more suitable for transistor design. That is, BJT transistor has a high sensitivity to changes in the applied signal. When the applied signal changes, the output changes accordingly. But this change in FET is very less compared to BJTs. That was a disadvantage of FET compared to BJT. But the main advantage of FET compared to BJT is the high input impedance. There is one more advantage to FETs. They are highly thermally stable. That is, they are unipolar. That means the current is flowing only because of majority charge carriers. So there is no minority current. If there is no minority current, the temperature dependency is very much reduced. So they have high thermal stability. And the most important advantage of FET is they are smaller in size compared to BJTs. You might have heard about integrated circuits, right? So we are going for smaller and smaller integrated circuits. So in their construction, FETs are more advantageous than BJTs because they have low size and high thermal stability. Okay, so this was an introduction about the field effect transistor. Now we can move on to the construction of an FET. So for construction and mainly for operation, we will be considering N channel FET. So you can see that there are three terminals here. So this is the structure of an FET. This blue colored layer is called an N layer, and you can see that this is covering most of the surface of our FET. So there is N layer, and two P layers are also doped in this material. So the construction will be, we'll have a semiconductor material. First it will be doped by N type impurity, and then here they will be doped by P type impurity. So where there is P and N joined, there we will have our junction. So this is a PN junction. This is also a PN junction. So there are two junctions here, just like BJT, and the top end of the N-type material is connected through an ohmic contact, and here we have a lead, and this terminal is now called drain, and we'll be using the letter D to denote drain. And the bottom part of this N-type material, there also we have an ohmic contact shown by this black color, and there also we have a terminal, and this terminal is called source. So there is drain and source. Now there are two more terminals. One is at this P end and one is at this P end. These are also ohmic contacts, this black colored things. So this FETs can be either 4 terminal devices or 3 terminal devices. So where we have taken the lead out, this terminal is called gate terminal, denoted by G, and this terminal is called body terminal, but in most of the constructions this body and gate will be shorted. So there is only gate terminal. So in this way we can say that FETs are, that is junction field effect transistors, are having 3 terminals or 4 terminals. So these terminals are drain, source and gate, and there can be a body terminal, but most of the time it is connected to the gate only. Okay, so this is the construction. There are 2 PN junctions. So where there are PN junctions, there will be depletion layer. So there are 2 depletion layers also. Okay, so this is the construction of a JFET. Now we can see how a JFET works. By that I mean we can see how it operates, and we will also see how the characteristics of this JFET looks like. Okay, so let's move on to the working. Now we have our JFET here with its drain, source. Now for the characteristics, we will be applying 2 conditions. First condition is VGS equal to 0. That means gate and source are short circuited. VGS means the voltage between gate and source. Now the second condition is VDS is some positive value. Okay, so we will connect a variable supply here which has a positive connected to VDS. So this is our VDD. This is the supply. It provides a voltage across D and S, and that voltage is VDS. This is our P-type material and this is our N-type material. Okay, so in this case we will see how the JFET behaves. So let's see what happens here. Now we have a PN junction here. This is a PN junction. This is also a PN junction. The P is connected to the source, which is connected to a negative supply. That means we can take it as our reference voltage. So P is connected to ground potential and N is connected to a positive potential. So what happens to the junction between P and N? What will be the biasing of the junction? Will it be forward biased or will it be reverse biased? We know that if N is more positive compared to B, that junction will be reverse biased. Let's call this junction J1 and this junction J2. Both junctions J1 and J2 are reverse biased. Now let's see what happens inside this. Okay, for that I am taking an enlarged view of this N channel FET. So here we have our gate which is connected to the ground now. Here we have our source which is also connected to the ground, and here we have our drain with a positive voltage. This is our p-type material, this is our n-type material. Now you know that in n-type material there are a number of electrons, right? Now this looks like a conductor, right? There are a number of electrons, they are free to flow, and when we apply a voltage like this, when VDS is positive, these electrons will be attracted by this drain, that is this positive supply, and they will start moving towards the drain. When electrons start moving towards the drain from the source side, we will get a current, and the current will flow through drain like this, let's call it ID, and the current will be here, let's call it IS. So this is drain current, this is source current. So when electrons are flowing in this direction, current will flow in this direction, right? Since there are no other currents, this ID and IS will be the same. Now let's see what happens around the junction. So I am removing these electrons and these currents. Now here we have our p-type material, here we have our n-type material. These junctions J1 and J2 are reverse biased. What you see here, this is the depletion layer when there was no supply. If we apply a voltage here, that means this N is more positive compared to P. So this junction is reverse biased. Again, this junction is also reverse biased. We have already discussed that. If a junction is reverse biased, the width of the depletion layer increases. So what we expect to happen here is there will be an increase in the width of the depletion layer, right? So our depletion layer has increased in width, so it will look like this. From what we have learned so far, we are expecting a uniform increase in the width of the depletion layer. But fortunately, this is not the case. What happens is, since our n-type material is now acting as a conductor, it has a resistance because there is a current flow through the n-type material. So there will naturally be a resistance between this drain and source. Let's say this is the resistance. We are assuming that this resistance is uniformly distributed across the length of this channel. Here, this is the channel. I have forgotten to tell you that. Now this n-type material is a channel between these two p-type materials. So this type of FET is called an n-channel FET. Okay, we will be analyzing an n-channel FET to understand the working of this. Then you can apply the same principles to a p-channel FET. So there is a resistance in the n-channel, and we are assuming that this is uniformly distributed. Now let's say we are considering a few points in the resistor, that is, we are dividing the resistance into equal parts. So I am taking these 4 parts of this resistance. Now we know that ID flows here. Let's say this resistance is equal to 1 ohm and the applied voltage VDS is equal to 1 volt. Okay, then this entire 1 volt will be dropped across this resistance, right? Across this 1 ohm we will have 1 volt. So if this entire resistance is 1 ohm, we have divided this resistance into 4 equal parts. So each part will have a resistance of 1/4 ohms, right? So the entire thing becomes 1 ohm. Now this 1 volt is distributed in this 1/4 ohms. So from ground to this point, what will be the voltage? It will be 1/4 only, right? This will be 1/4 volt. From ground to this point, what will be the voltage? That is the voltage at this point. At this point, the voltage will be 1/2 volt, because a 1/4 volt is dropped here, a 1/4 volt is dropped here. So the total voltage here is 1/4 plus 1/4. And at this point, we will have a voltage of 3/4 volt, and here we will have 1 volt across this point and ground, right? So if you look at the resistor, look at the points we have considered, each point has a different positive potential, right? Now this point is close to the junction at here, this point is close to the junction here, and this point is close to the junction here. So at different points of the junction, we have different reverse potentials. The width of junction here is affected by a voltage of 3/4 volt. The width of junction here is affected by a reverse voltage of 1/2 volt, and the width of junction here is affected by a reverse voltage of 1/4 volt. That means the increase in width of the depletion layer will be different in these different points. So let me show that here. I am removing the resistance. Now we have a potential gradient in this N channel, that is the potential is different in different points of the N channel, right? So here at the top, that is near the drain, we have a higher reverse bias, and near the source we have a lower reverse bias. Where the reverse bias is more, the junction will have more width, and where the reverse bias is less, the junction will have less width. The same happens to this junction also. So our junctions will look like this, and in here also, in the p-type material also, the same happens. So this is the width of the new junctions. This is the width of the junction when we apply a positive VDS. Okay. Now let's say this width was, when VDS is low, this width is low. When we increase the value of VDS, this width will start to increase. So if you look at the figure, you can see that at a particular VDS, this and this will collide. Now where there is this junction, we know that in the depletion layer there are no carriers, right? There are no majority carriers, there are no minority charge carriers, there are only heavy ions which cannot constitute to current flow, right? So if this width increases, the current through this channel is choked. It is being forced to reduce, and it will not reduce because we are increasing the potential and the resistance in this is constant. So the current will increase, but it is constricting the flow of this electrons. If we increase the value of VDS at a particular value, at a particular potential, these two depletion regions will collide. What happens if they touch? If this depletion layer and if this depletion layer touch, now there is no path for electron to flow, because this depletion layer will block the flow of electrons. If there is no path for electron to flow, what happens to the voltage drop in this N channel? There is no voltage drop. If the current falls to 0, there is no voltage drop. If there is no voltage drop, then this depletion layer width will decrease and it will go back to this level. And what happens then? The current will start to flow, right? But this cannot happen. That is, they will get so close but never touch. Okay? At that point, at that potential onwards, the current will remain a constant at a saturation level. So this is the operation of a FET. So when these two depletion layers almost touch, that phenomenon is called pinch-off, and the potential that is causing this pinch-off is called the pinch-off voltage. Actually, the term itself is a misnomer. Pinch-off means we are pinching off the current, but that pinching off of current never occurs. There is a point when the current remains constant. Even if we increase VDS, the two junctions will not touch each other. So we'll now see how the characteristics of this FET looks like for VGS equal to 0. And for the characteristics, obviously we have a voltage and current. At the x-axis we have VDS because that is the value we are varying. Now on the y-axis we have ID, the current, right? So initially we know that before pinch-off our FET will behave like a resistance, and once pinch-off occurs, this current will stay the same. So this is the pinch-off voltage Vp. Okay, Vp is the particular value of VDS where these junctions almost coincide and current becomes a constant. If we increase VDS beyond a limit, what happens? Breakdown occurs in both these junctions and therefore we will lose control of this JFET. So this is the breakdown voltage. Since VDS is a reverse bias to the junction, a breakdown occurs. Okay. Now this current is called IDSS, or the saturation drain source current. And the voltage at which this current starts flowing is called pinch-off voltage. And this is the characteristics for VGS equal to 0. What happens if we apply a negative VGS? What happens if VGS is less than 0? If VGS is negative, that means these P layers are connected to a negative supply. So even before we give some VDS, these junctions will be reverse biased. So if we apply a positive VDS, what happens to the junction? It is already reverse biased. Its reverse bias will increase and a pinch-off will occur. So when VGS is negative, pinch-off will occur for a lesser value of VDS compared to the case when VGS was equal to 0 volt. Okay. So if we increase the negative voltage of VGS further and further, the VDS for which pinch-off occurs will decrease further and further. So the characteristics for VGS less than 0 will look like this. This is our ID and VDS, and this was the characteristics for VGS equal to 0 volt. If we increase VGS in the negative direction, if VGS, let's say VGS equal to -1 volt, then the characteristics will look like this. And if we further increase VGS in the negative direction, it will look like this. And let's say this is the characteristics for VGS equal to -3 volt. And if VGS equal to -VP, the pinch-off will occur even before we give VDS, right? So essentially, it means that ID will be 0 for any value of VDS before breakdown. So this is VGS equal to -VP. This is the characteristics. Now if we look at the pinch-off voltage, this is where pinch-off occurs for VGS equal to 0, and we can draw a locus for the pinch-off for different VGS. So the locus for pinch-off will look like this. Now this is the locus of pinch-off voltages. Now this characteristics can also be converted into 3 parts, where VGS equal to -VP and ID is equal to 0. This can be called the cutoff region. Where ID is increasing linearly with VDS, this is called ohmic region. And in the ohmic region, this FET can be used as a voltage controlled variable resistance. And this region is called the saturation region after Pinchoff. So these are the three regions of operation of a junction field effect transistor. In the ohmic region, our FET will behave as a voltage controlled resistance. And the value of this resistance RD can be found out using this equation. RD is equal to R0 divided by 1 minus VGS divided by VP the whole square, where R0 is the value of RD when VGS is equal to 0. When VGS is equal to 0 volt, what we get here, that is this resistance, is R0. We can show it here. If we take the slope of this line, that will be the reciprocal of this resistance. So take the slope, then take the reciprocal, you will get R0. And this RD can now be calculated using this equation. Okay. Now the symbol of an FET looks like this: the substrate, then the three terminals. This is the gate, this is drain, and this is source. Now depending on whether it is N channel or P channel, there will be an arrow pointing in or out. If this is N channel, then gate will be P. That means an arrow will be pointing in like this. So this is N channel JFET. If it is P channel, the symbol will look like this: drain, source, gate, and an arrow will be pointing out. And this is P channel JFET. This is the symbol for P channel JFET. And normally there will be an envelope here. Okay, so this is the symbol of an N channel JFET and a P channel JFET. Now there is one more characteristics. The characteristics we saw, it is the output characteristics, right? There is ID versus VDS, that is output current versus output voltage. So this is the output characteristics. This characteristics is also called the drain characteristics, but the second characteristics is not called the input characteristics, because you can see that there is no current flowing here. Okay, VGS, if VGS is 0, IG is equal to 0. In all operating conditions, this junction is reverse biased. That means there is very limited amount of current flowing from gate to the drain or source, from gate to the source. Now the reason is the reverse biased junction. Even in reverse biased junction, we know that minority charge carrier flow is there. So a very limited number of minority flow will be there, but compared to ID, that current will be very less. So we need not consider that. For all our considerations and explanations, the gate current is ultimately equal to 0. Okay. So because of that, there is no input characteristics. If there was an input characteristics, it would be between VGS and IG. Since IG is 0, there is no input characteristics. But there is a characteristics between VGS and ID, because ID is controlled by VGS, right? So that characteristics is called transfer characteristics. And this transfer characteristics follows an equation and that equation is given by ID is equal to IDSS into 1 minus VGS by VP the whole square. This is the equation for ID in terms of VGS, because VP and IDSS are constants. This IDSS is called the drain to source saturation current, VGS is the gate to source voltage, and VP is the pinch-off voltage. VP and IDSS are constants, so ID depends on VGS. Okay, this equation was derived by a scientist called Shockley, and thus this equation is called Shockley's equation. Now this is the equation between the control variable and the controlled variable, because the control variable is VGS and controlled variable is ID. So the transfer characteristics is a graph that shows this relation, and that graph looks like this. You get this graph for negative values of VGS. So here we have ID and here we have VGS. When VGS equal to 0, you will get ID as IDSS, so that will be this point. If you substitute different values for VGS, you will get different values of ID, all positive, because VGS is already negative, so negative and negative becomes positive. So you will get a graph like this. When VGS equal to VP, this current becomes 0. So this is the transfer characteristics of a JFET, and this equation is very important in case of a JFET. Okay, with that I'm winding up today's lecture, and we'll see more of JFET in the upcoming lectures. Until then,